So let's have a look at the 2017 acid-based question. It came up with question 9 as a full question worth 50 marks. So they started off by asking us some of our standard definitions that we came across in 5th form. So they're asking us for a Bronsted-Lowry base, okay, which we know is a proton acceptor. And they've asked us to define a conjugate pair. If I can spell correctly. So a conjugate pair is a pair of two substances which differ by a H plus. Or by a proton. Okay, and then they ask us to write the conjugate acid of water. Okay, so we know that when a conjugate acid is formed by a base behaving like a base. And we've already said that a base is a hydrogen acceptor or a proton acceptor. So that water, when it accepts that proton, is going to become the hydronium ion or the H3O plus ion. Okay, part B then asks us to define pH. So we're well used to this definition by now. So pH is equal to minus log to the base 10 of the hydrogen ion concentration. So now they give us three solutions: sulfuric acid, hydrochloric acid, and methanoic acid. They are all the same concentration, but they've got different pHs. Okay, so I'm just going to fill in the pHs above the actual names here. So we know that the sulfuric acid is 0.7, the hydrochloric acid is 1, and the methanoic acid is 2.37. So I've just written them above the names just because sometimes it's a bit easier to keep track of the information that they give us. So they're the same molarity, but they've got different pHs. And the first question that they're asking us here is to account for the difference in these pH values in terms of hydrogen ions. And they're asking us, first of all, to compare the hydrochloric acid and the sulfuric acid. So we've got 0.1 molar hydrochloric acid, and we have got 0.1 molar sulfuric acid. Okay, and we know that the pH of the hydrochloric acid is equal to 1, and the pH of the sulfuric acid is equal to 0.7. So why is the sulfuric acid lower than the pH of hydrochloric acid? Well, let's have a look at their dissociation. We know they're both strong acids, so they're going to fully dissociate into their ions. H2SO4 then is going to dissociate into H plus and SO4 2 minus. But we've got two hydrogen ions there. So if we compare the hydrogen ions that are produced by the HCl and the sulfuric acid when they dissociate, you can see that for every one molecule of hydrochloric acid, we get one hydrogen ion produced. And we call that monobasic. Whereas with the sulfuric acid, you can see that for every one molecule of sulfuric acid, we get two hydrogen ions produced, and we call that dibasic. Now, how does that affect our pH? Well, we know that the higher the pH, the higher the hydrogen ions, or the more hydrogen ions, the lower the pH. So we've actually got twice as many hydrogen ions being produced by the sulfuric acid, which means that it has a lower pH. So that's the first comparison that they asked us to do. The second comparison then is between the 0.1 molar HCl and the 0.1 molar methanoic acid. Okay, so we know that the pH of the hydrochloric acid is 1, and the pH of the methanoic acid is 2.37. Now, what is it about the methanoic acid that means that it has a higher pH than the hydrochloric acid? Well, we know that the hydrochloric acid is a strong acid, which means that it's going to fully dissociate into all of its hydrogen ions. Whereas the methanoic acid is actually a weak acid, and we know that from our organic chapter. Our organic acids are all generally weak acids, which means that it does not fully dissociate into hydrogen ions, HC. So let me start that one again, HCOO minus. So because this methanoic acid only partially dissociates, even though they start off with the same concentration, the methanoic acid is going to produce less hydrogen ions, which means it's going to have a higher pH. Now, there is another way that you could have tackled this question. You could have actually just used the pH formula, equals minus log to the base 10 of the hydrogen ion concentration. And you could have actually just calculated the hydrogen ion concentrations, but you would have still needed to compare the numbers and discuss the monobasic versus the dibasic in the first part and the strong versus weak. But if you were kind of not sure where to start, you could have always calculated the hydrogen ion concentrations just to give you a starting point. Okay, so now part 3, I'm going to move down here. Part 3, then, they ask us to calculate the value of the acid dissociation constant Ka for methanoic acid. So we know that we've got 0.1 molar methanoic acid. Okay, it's a weak acid, so I know I'm going to have to use my equation that takes into account the Ka and the Ma. Now, how am I going to calculate this Ka when I know the Ma, but I don't quite know the hydrogen ion concentration yet, but I can calculate it using what I've just written up here. So I know that the pH is 2.37, so it's 10 to the power of minus 2.37, and that will give me a concentration of hydrogen ions to be 4.27 by 10 to the minus 3 moles per liter. So now I can sub that into my equation my equation that incorporates the Ka and the Ma. So I have 4.27 by 10 to the minus 3 moles per liter is equal to the square root of the Ka times the molarity, which is 0.1. So let's square both sides, and I end up with 4.27 by 10 to the minus 3 to be squared is equal to 0.1 Ka. So my Ka is equal to 4.27 by 10 to the minus 3 to be squared all over 0.1, which will give me an answer of 1.89 by 10 to the minus 4. So that is my Ka for part 3. Now for part 4, they're asking us to calculate the pH of a 0.05 molar methanoic acid solution. So let me just pause the video for 1 second. Okay, sorry about that. So the next question, as I said, asks us to calculate the pH of a 0.05 molar solution of methanoic acid. So we'll just do that over here. So we have got 0.05 molar methanoic acid. So now that we've calculated the Ka, again, what we'll need to do is calculate the new concentration of the hydrogen ion, because we've changed the overall concentration, which means that concentration of our hydrogen ion is going to change. So we're going to use the Ka that we've just calculated to be 1.8197 by 10 to the minus 5, multiplied by the Ma, which is 0.05 this time. So that will give us an answer of 2.4 38 by 10 to the minus 3 moles per litre of my hydrogen ion. Now to calculate the pH, we've got minus log to the base 10, the hydrogen ion concentration, which when I plug in that answer, 2.438 by 10 to the minus 3, that gives me an answer of 2.61 for the pH. Now the final question is asking us to draw a pH curve. So they're asking us to draw the pH curve between 0.1 molar sodium hydroxide and 0.1 molar methanoic acid. Okay, so we're going to draw our axes. So we've got pH on the y-axis. I'll put my pH of 7 in there. And I've got on the x-axis the volume of base added. So remember, when we're drawing our pH curves, we start off with the acid in the conical flask or the beaker, and we add base to the acid. So we've got our y-axis, volume of base added in centimeters cubed, and we have got our pH on the y-axis of 7. Okay, so we are adding this to 0.1 molar methanoic acid, and we know that the pH of that methanoic acid is 2.37. Okay, so we have a pH of 2.37. So our pH curve is going to be starting off somewhere about here. Let me change the color of that pen. Okay, so our pH curve is going to start here. Now remember, this is just a sketch. Now, we have got 25 centimeters cubed of 0.1 molar methanoic acid. So that means that because they're the same concentration, 0.1 molar sodium hydroxide and 0.1 molar methanoic acid, neutralization is going to occur after 25 centimeters cubed of the base have been added, because each centimeters cubed of the sodium hydroxide and the methanoic acid contain the same number of moles. So after adding 25 centimeters cubed of the sodium hydroxide, we should have neutralization of the methanoic acid. So we know that we're going to get a gradual increase of pH as we add our sodium hydroxide, and then we're going to get a significant jump in pH where we have neutralization, and then we're going to keep adding the rest of our sodium hydroxide because we were told that we had 50 centimeters cubed. Okay, so what are we looking for on this graph? We need to make sure that we have the correct starting point. So we start off at the correct pH. Now I know I'm only sketching it there. Yours will be a little bit better, but they're only asking us to draw the diagram. It doesn't have to be a work of art, as long as you have your pH starting at approximately 2.37. You have neutralization occurring at 25 centimeters cubed. You've got that steep part of the graph that indicates neutralization, and then we have that leveling off of the graph to finish off at a high pH because we've got a strong base there. And then our graph finishes at 50 centimeters cubed because we're told in the question that we've got 50 centimeters cubed of our sodium hydroxide. Now we're asked to name a suitable indicator for the titration between these two solutions. Okay, so we have a couple of options for our titrations. Now we know that we've got methyl orange, which changes color between 3 and 5. Okay, so that has a range. That's my methyl orange. That has a range between 3 and 5. We also have, I know my graph is not fantastic, we also have litmus, which has a range between 5 and 8. But that wide range makes litmus a little bit less reliable. And then we've got phenolphthalein, which is going to change between 8 and 10. So just label that P instead of writing the whole thing out. So we want a color change that coincides with the majority of the steep part of our graph. And in this case, we would use phenolphthalein because we've got a weak acid and a strong base. So the majority of my steep part of my graph, and perhaps I should draw that a little bit steeper. So when we have a weak acid and a strong base, the majority of the steep part of this curve needs to be above 7. So for this titration, we would need phenolphthalein because its range is 8 to 10 and its color change coincides with the steep part of the graph. Okay, so that brings us to the end of the 2017 acid-base question. As I said before, any questions, just send me an email.